Okay, so here's another application of the squeeze theorem. I like to look at, let's say, this one, 38. On 107, and we have 2x less than or equal to g of x less than or equal to x to the fourth minus x squared plus 2 for all x. We're asked to find limit of g of x as x approaches 1 from either side. I don't even have the function. The function is not even given to us. But yet we are asked to find the limit as x approaches 1. But we do know that this function is squeezed between f of x and g of x for all x. No matter what I pick, this function is squeezed between these two. So the first part of the squeeze theorem is already given to us. We do not have to find the functions that squeeze the middle one. But now what is the second part of the theorem? In the second part of the theorem, I have to find limit, yes, from, excellent. And I also have to find the limit as x approaches 1 from, yes. If these two happen to exist, and if they happen to be the same number, what do you conclude about limit of g of x as x approaches 1 by the squeeze theorem? As that number. Okay, what do you think about the first one? What do you think about the second one? 2. What do we conclude then? By the squeeze theorem. So this is another application in which we were not even given the function. We had no idea what the function was. But since we were given the information that it was squeezed between two other functions, we were able to find the limit. Okay, I would like to discuss one absolute value limit, and then we can move on. There are so many different types of limits. And I stopped counting, and 8, 9, 10. I dropped them once. You don't want to know. It took me some time to put them in order, so I'll never do that again. Okay, so let's say problem 46 on page 107. So limit as x approaches 0 from the right, from 1 over x minus 1 over the absolute value of x. We are asked here to simplify the function fully without absolute value before we apply the limit. So as a requirement, simplify the function first, of course fully, before we apply the limit. Okay. In these situations, we have to start with this. That's our starting point, the absolute value of x. Do we remember what are the options for the absolute value of x? The formal definition of the absolute value of x. Yes? Say it again. I couldn't hear you. True. What are the two options? For x greater or equal to 0 and for x less than 0. What are the options? Yes. Indeed. Perfect. So if x is a positive number or 0, the absolute value can be replaced by x. If x is a negative number, the absolute value can be replaced by negative x. Do we understand this definition? Any questions on this definition? So this is the formal definition of the absolute value because x is not given to us. And we cannot work with the absolute value of x. We have to simplify it. And there are two possibilities. If for the absolute value of x are two possibilities, for the function, I will find two possibilities. Ready? Okay. So now let's simplify 1 over the absolute value of x. So I have this piece. Now I'm working on this piece. And then I will be working on the entire function. So this has two options because the absolute value of x has two options. Can anyone give us those two options? 1 over x or negative 1 over x, correct? But now I have to be very careful. X here was not in the denominator, but x here is in the denominator. So then I have to make a change here. What is it? Very good. Just strictly greater than 0 and x less than 0. Is that clear? Is that clear, the change from here? Okay, perfect. Now let's put the entire function together. 1 over x minus 1 over the absolute value of x. Carefully give me two options, for greater than 0 and for less than 0. Which is? Excellent. And the other option is, careful, minus minus, plus 1 over x. An apple plus an apple is always 2 apples. So we simplified the function fully. This is the simplified form of the given function. And now we are definitely ready to present this limit. From which piece? We are asked to find the limit as x approaches 0 from the right. Which piece is 0 from the right? Top or bottom? Of course. What is the answer? 0. What if the problem was we're asking us to find the limit as x approaches 0 from the left? Which piece? Good. 2 over x. What would you say? Remember the graph of 1 over x. 2 over x is the same thing. 1 over x or 2 over x? Very good. What if we're asked to find the limit from either side? It does not exist. Correct. What about x equals 0? Is that a vertical asymptote or not? Yes. If at least one or the other, or even both, it's fine too. But if at least one or the other is a negative or positive infinity, then x equals 0 is a VA. Very good. Is there anything that you can think of here, or can I continue? Is there any other limit that you would like to work on? Or can I continue? Is there any other type of problem that you would like to do or look at? Do we need another absolute value, or we move on? Are we okay with the absolute value? Correct. Of course. Would you like to choose? So here they are. All these are with absolute value. There is one here with absolute value at the bottom, right here. That's about it. That's all I can see. And we worked on 46. Okay, which we want to do 43, this one? Very good. So let's work on 43. at 43, we have limit. As x approaches, I think it's 5.5, I'm sorry. 1/2 from the left of 2x minus 1 over the absolute value of 2x cubed minus x squared. There is, in my opinion, in this book, not too many very plain, simple problems. They all have different things, all have some sophistication. Okay. We have to simplify the function first. F of x first. This is f of x, of course. We start where? With the absolute value, of course. Good. So this is 2x cubed minus x squared. Remember, the absolute value symbol is not a grouping symbol. You can remove stuff. You can put stuff in. You cannot distribute. You cannot take stuff out. You can't. Okay. But I do see something inside. What do you think I see inside the absolute value? Remember, factor and simplify are the key words. What do I see inside? I see what? I see an x squared, and then I see a 2x minus 1. Correct? Yes. I see an x squared as a common factor in both terms. I pull it out. There is a property of the absolute value, actually two. The absolute value of a product is the product of absolute values. Also, the absolute value of a ratio is the ratio of the absolute values. These are properties of absolute value. Prop of absolute value. We're going to use it now and in the next section too. Okay, so then I will definitely use the first property and write the absolute value of x squared times the absolute value of 2x minus 1. But do I really need the absolute value of x squared ever? No, I do not. So all this work, I didn't even get anywhere yet, was to simplify this as much as possible. It has an absolute value. It will have two options. Anything that has absolute value in it, it will have two options. So then, finally, after some simplification, I will write that x squared times the absolute value of 2x minus 1 has two options. I want to come back to the formal definition of the absolute value because I want to emphasize something. We are looking now at the absolute value of 2x minus 1. The formal definition with 2x minus 1 inside. That's all I need to do. I need to mimic the definition in which I have 1, 2, 3, 4, 5 identical quantities. The only difference is here. 1, 2, 3, 4, 5. And that's a minus in here. So now, can you please give me those 5? I have 1. I want the second, the third, the fourth, and the fifth. What will you say? X squared to x minus 1. Very good. When 2x minus 1 is greater than or equal to 0. That's what we just have here, right? 2x minus 1, 2x minus 1, 2x minus 1 greater than or equal to 0. Now I need 2x minus 1 and 2x minus 1, but of course I have a little extra quantity that I have to carry on. I don't have a choice. So please keep in mind, this definition does not only refer to x. It refers to any expression with x. But please be careful. how you simplify these. This, once you solve this inequality, you do not have to solve the second one. If this is to the right of 5, this must be to the left of 5. If this is to the left of -1, this must be to the right of -1. Do not ever waste your time to solve the second inequality ever, okay? So, finally, we have the simplified form, x squared 2x minus 1, x greater than or equal to 1/2. I moved -1 and divided by 2. Negative x squared 2x minus 1. I refuse to even look here. I will copy exactly the opposite, less than 1/2. If this is greater than or equal to 1/2, this must be less than 1/2. All this work, and I haven't even finished. I only worked on the denominator. Now I will put everything together. So now we want 2x minus 1 over x squared, the absolute value of 2x minus 1. And there must be two options. I can no longer use the equal symbol because now this quantity is in the denominator. So greater than 1/2, less than 1/2. Two x minus 1 over x squared times 2x minus 1 will give us what? One over x squared. Awesome. Great job. 2x minus 1 over negative x squared times 2x minus 1 will give us 1 over x squared. So now we want to determine the limit from this, the simplified form, when x approaches 1/2 from the left. So limit as x approaches 1/2 from the left. Which branch? The bottom one. Very good. So -1 over x squared. And what do we get? This is exactly when I drop the limit operator. So I have -1 over, in the denominator, 1/2 squared is 1/4. And the answer is -4. Any questions? A problem like this is not feasible for a test or a final exam. Yes, it took me a while to explain, but still, it still took me 5 minutes. I mean, it's way too long. Okay, way too long, in my opinion. Because I'm testing one problem with, it will take you several minutes. But it's good to see it and to understand how we use the absolute value, how we simplify the function, and how we finally get the limit. Is that clear? Okay. So I'd like to at least start the next section, which is 2.4. Going back to, where's my syllabus? Yeah, it's right here. Back to the schedule at the very end. So our tentative schedule says test 1 from chapter 2 on the 18th. So I'm trying to make progress. This is, I think it's, what is it today, the 4th? So it's 2 weeks from today. We'll see if we can. Okay? So we only finished 3 sections, and we have still including 2.8. So we are moving on to 2.4. Now, this is a formal definition, and it's called the precise definition. Precise definition of the limit. Also called the epsilon delta definition of the limit. So we can say the precise definition or the epsilon delta, we mean the same thing. this is the only proof that you're going to see this semester. I do insist that we understand how to present the definition for a linear function, which is absolutely the easiest possible. Not the infinite limits, just the limit from either side. Only for simple functions like linear, but I would like you to be able to reproduce this. It's initially it will look like, but it will be very easy. So just bear with me. Okay. So let's take a look at this scenario. We have a function. This is f of x. And of course, this is what we know now already. What is it? Good. And of course, we know what this is. Good. Of course. And when we write limit of f of x as x approaches a from the graph, you will say it's very good. Obviously, this is all clear. What does this mean, the precise definition in epsilon delta? What is this? Okay. This is really based on understanding when the limit exists, when it doesn't exist, and it's really imagining that you are zooming in. So imagine that you're zooming in and zooming in and zooming in and zooming in. So let's start. This symbol is the double equivalency symbol. Double equivalency symbol. What does this mean? It means that I can start here and get that, or I can start here and get that. It goes both ways. What does this mean? It says that the limit of the function as x approaches a from either side exists, and it's a number L. I'm going to repeat this definition several times till we understand it, and then we'll write it down. So the limit of f of x as x approaches a exists, it's a number. That means that for every epsilon positive, what is this and where is it? Epsilon is an interval that we will create around the limit. Symmetric interval around the limit. This piece, this point here, will be L plus epsilon. Can anyone give us this if the interval is symmetric? L minus epsilon. If the limit exists when x approaches a from either side, bless you, and it's L, it means, automatically it means, that for every epsilon positive, it can be this big, or it can be this big, or it can be this big, or it can be this big, but we really want to zoom in and zoom in and zoom in. Because outside, if we are far away from it, even if the limit does not exist, I may find the intervals. So we want this to be very small as we wanted it to be, we can make it, right? For every epsilon greater than 0, we will find, and this is a key word, a corresponding, not just any, a corresponding delta positive. What is delta and where is it? Careful, please watch. At this point, I draw a horizontal line. It meets the function here. At this point, I draw a horizontal line. It meets the function here. And now I go vertically. I must choose. For some reason, they kind of got the same measure. They will not be the same measure to the left of A and to the left of Y, but to the right of A. But in my graph, kind of look as if they are the same. They are not. I'm going to say that this is the smallest, and I'm going to say that this is larger. This will be A minus delta, and this will be A plus delta, and this is delta. Okay, we start from scratch again. If the limit from f of x as x approaches a is a number, exists as a number L, it automatically means that for every epsilon that I pick, small or big, whatever I wanted it to be, I will always be able to find a corresponding delta greater than 0 near A, such that we're almost done with the definition, but I keep repeating it so we don't forget where we are starting from and where we're going. So for every epsilon, I will find a corresponding delta, and I'll explain why I chose the smallest in a minute, such that whenever we pick x near A, and there is a condition that I have to write in parentheses, and I'll come back to it, the absolute value of x minus A is less than delta. This means that if I pick x here, the distance between x and A has to be smaller than delta. This distance is smaller than delta. If I pick x here, the distance has to be smaller than delta. However, if I choose to pick x here, x will not be within delta from A. So every time I pick x near A, can anyone tell us where the function value will end up? If this is x, this is f of x. Where will it end up? Close to L, not further away than epsilon. Okay? Whenever we pick x near A, f of x must be, or must fall, within epsilon away from L. Within epsilon away from L. Why does this happen? Because the limit exists. And this is a very important keyword. Let me come back in a minute. I just want to show you a counterexample so you understand the mechanism. What do you think about the limit of this function as x approaches A from either side? D&E, we say, right? We agree? But what if I do this? L plus epsilon, right here, L minus epsilon. Look. And I'll choose the smallest of the two, and I found delta. How come the limit doesn't exist? I can show I found an epsilon, L plus epsilon, L minus epsilon, such that every time for this epsilon, I found a corresponding delta. Of course, I have to choose the smallest, because if I choose this, then it will be outside. The smallest of the two. I measure these two, and I choose the smallest. And now, when I pick x, f of x will be within epsilon away from L. I claim that the limit exists. The keyword is for every epsilon. I picked one, and I showed that the limit exists, but it doesn't work for all. Look what happens if I choose this epsilon. I will never be able to find an interval around A? It doesn't exist because the limit doesn't exist. So the keyword, one more time, the keywords are for every epsilon. The limit exists because for every epsilon around L, I will find a corresponding delta around A, such that when I pick X within delta away from A, f of X will be epsilon away from L. And this can go on forever for any epsilon because the limit exists. Here, it exists for a particular special epsilon, but the limit does not exist because it does not work. The mechanism does not work for every epsilon. So let me just show you a couple of mathematical notations so we don't have to write all this. But now I would like to explain this. So the absolute value of x minus a means the distance between x and a. So when we pick x, the distance must be less than delta. On this side, we are going to write strictly greater than 0. And you could say, wait a minute, this is always positive, it's a distance, why do you need this? This only says that x cannot be a. There's no equal symbol. So in short, this is how we write. You don't have to write those symbols. I think they're easy, but you don't have to write them. So here is the formal definition now. The epsilon delta definition. Limit of f of x as x approaches a from either side is L. This is equivalent to, for every, I will write down all these symbols for you in a minute, for every epsilon greater than 0, I will find there exists a corresponding delta greater than 0, such that 0 less than the absolute value of x minus a less than delta will always imply that the distance between f of x and the limit is less than epsilon. Yes, it sounds and looks gibberish, but you'll see. We have time. Yes, we have 5 minutes to work on one problem. So let me write down these symbols. This symbol means for every or any. For every, for any epsilon positive. This symbol, there exists. Or you can say, I will find a corresponding delta positive. This symbol, such that. And that's it. 3 symbols. So let's pick a very simple example. I'm not asking you about quadratics, nothing, just linear. Okay, so we have 16 on page 117. Limit x approaches 4 from 2x minus 5 is 3. I need this in front of us. Is this true? 4 times 2 is 8. This is polynomial. I'm allowed to plug in. 4 times 2 is 8. 8 minus 5 is 3. Agreed? So I will write the definition. I have to write it all the time. For every epsilon greater than 0, I will find a delta greater than 0 such that, careful now, 0 less than x minus. Now I have to identify this. What is A in our problem? Excellent. Less than delta will imply, what is f of x in our problem? 2x minus 5 minus, what is L in our problem? Less than epsilon. Okay. We start at the end. We start here. Combine like terms and tell me what to write. Less than epsilon. I want this. So look inside and tell me what you would do. Of course. I cannot pull anything out before I write the property that we just reviewed today. The absolute value of 2 times the absolute value of x minus 4 less than epsilon. But now, what is the absolute value of 2? 2. Now I can write 2 times the absolute value of x minus 4. I am allowed to peek. I have x minus 4. Sorry. Less than delta. So what should I do to both sides to have just the absolute value of x minus 4 on the left? What? What will you do to both sides to just get x minus 4 to the left-hand side?
Divide by 2.
Of course. So now please compare this to this. And tell me how much is delta. And remember, delta will always depend on epsilon. So how much is delta? Compare this to this and tell me how much is delta.
Epsilon over 2.
Thank you. This is it. What does this say? If epsilon is 0.1, how much is delta? 0.1 over 2. If epsilon is 0.01, how much is delta? 0.01 over 2. And I can go on forever. Why? Because the limit exists. For every epsilon I pick, you will say, no problem. I'll divide it by 2 and I'll give you delta back. Why? One more time. Because the limit exists. So if epsilon is 0.1, delta will be 0.1 over 2. If epsilon is 0.3, delta will be 0.3 over 2. If I want to go zoom in closer and closer to L, if epsilon is 0.0001, delta will be 0.001 over 2. And I can continue forever because the limit exists. That's all I want you to do. And of course, we'll have more examples.